Hi everyone, my name is Michael Payton-Jones and I'm here with Jan Muller, who you're going to be hearing a little bit from a bit later on. We work on the Plutus team and we're going to tell you a little bit about what we've been working on in recent time. And so before we start, I need to clear up a bit of false advertising. So you've all been invited to the Cardano Virtual Summit Shelley edition. Shelley's basically done, right? It's out the door. It's all fine, all sorted. Everybody's really thinking about Goguen, which is the next bit, comes after Shelley, and that is what we are going to be talking about. This is all Goguen era stuff. So I would like to welcome you to the Goguen edition of the Cardano Virtual Summit, which is much more exciting than the other one. Don't tell them I said that. The first question that you probably have in your minds, or at least I think you should have in your minds, is what are we doing, and more importantly, why are we doing it? Like, what is the point of Goguen in general? To be honest, Shelley, okay, decentralization, right? You actually make your blockchain work with lots of people doing bits independently. But what actually is the point of Goguen and of the all this Plutus stuff? Fortunately, I think there's a relatively clear answer to that, and that is applications. And that's obviously very vague, so I need to unpack that a bit. So I'm going to try and give, my understanding of what an app that means in our context. So what is an application? These things that we care about. And I think an application is, first of all, it's some kind of program that interacts with Cardano in some way. We'll talk a bit more about what the interesting ways of interacting with Cardano are a bit later. It's something that's actually written by developers in the community, so it's not just written by OHK. It's not something that you have to, be able to write a consensus algorithm to be able to do. And it's also used by lots of people. It's potentially a consumer product that many people use and run on their computers or mobile phones or something. And the picture this paints is that we've actually got an application development ecosystem that is built on top of Cardano, but isn't blocked by IOHK or anything. The developers can make their applications, they send them to users, and they can actually do stuff they want to do, and are empowered to do that. And so what we're going to do in the rest of the talk is just go through each of these points in a bit more detail and explain how that plays out in the context of Cardano and how that's influenced the design for the Plutus platform and what you'll have to look forward to. Okay, so to begin with, what are these programs we're talking about? What do they do? So, what's an application? But what's an application? Qua program. So in the beginning, in all diagrams, there is a single box in the middle. In this case, it says application. This is your program. It's running on a computer somewhere. But it doesn't you don't want to just sit there generating heat. It'll probably talks to some other things. So let's imagine a very simple example, part of a payment processing workflow where you maybe have, the web server that backs your web app, and user takes some action there, and as a result, you need to send them some money. So it tells your application, it says, please can you send the user some money? Application says, yes, I will achieve this with the power of the blockchain, and does this by submitting a transaction to the blockchain. And there's information the other way, so the blockchain says, yes, your transaction was submitted or confirmed or whatever it is you care about. Then you tell the web server, you say, yes, I sent the money, it's all done, and then they show a little pop-up to the user or whatever it is that they do. And this is the business logic of your application. But as ever, the business logic is only a bit of it, right? There's always tons of other stuff you have to worry about, and the same is true here. So for starters, in today's world, consumers expect to have multiple instances of their applications. Maybe not this payment processor, but this is something that an end user might use it. But they might have one instance running on their phone, one instance running on their desktop, one instance running on a tablet, and they would really like those all to be in the same state. They expect to just be able to switch between them and have it work. So you need to do some kind of state synchronization between those two, and better be good, because you don't want to do the same thing twice, send someone money twice. That's your users would not be happy if that happens. You've also got to deal with just all the other admin stuff that comes with running a production application. You've got to actually deploy these things. You've got to get your program onto the computer where it runs in some way that your DevOps team is happy with, and you don't want them to be unhappy with you. Otherwise, you're going to have a bad time. You want to back it up because, well, I'm sure your infrastructure and your code is perfect and there will never be any problems. You might just want to take some backups just in case so you don't lose all your money. And you want to have some kind of monitoring because you want to know when things are going wrong, which I'm sure they won't, but just in case. And then you probably also want to also be extracting all of your routine logs and throwing them into your favorite cloud enterprise logging service bucket, or whatever it is you use. So it's just, as ever, there's just quite a lot of bits to this, and even the bits that seemed initially kind of simple. So this interaction with the blockchain, where all we do is we just submit transactions, it's not quite that simple as a user. And one of the more complicated things that can happen is when there's a rollback. So we do have rollbacks in Cardano, and actually these are quite tricky to deal with as a user in general, and also particularly as an application author, because you've got to make your program smart enough to do the right thing when this happens. So I just want to spend a little bit of time showing you an example of that to kind of hammer this point home. So let's imagine we're doing a kind of simple three-way exchange. So we have three parties, Alice, Bob, and Carol. Alice and Bob want to do a trade. Maybe Alice is going to give Bob some special tokens that mean something, and Bob is just going to pay for them in ADA or something. But Bob is skint, and so Bob phones up his friend Carol and says, "Carol, can you please cover me for this?" And Carol says, "Sure, fine." There's a very simple protocol here. Alice sends Bob whatever it is she's promised to send Bob. Carol can then see on the blockchain that this has occurred, and then Carol performs her part and sends some whatever she's supposed to send to Alice. There's a bit of trust here, obviously, because Alice has to trust that Carol is actually going to follow through and not just say, "Ha ha ha, I'm going to leave now that you paid Bob." And we can do a little diagram for this. So time goes downwards. So we start off, Alice pays Bob in some transaction T1. Sometime after that, Carol observes it. Some time after that, Carol pays Alice in some transaction T2. But then, suppose there was a rollback. Now, the way rollbacks work in Cardano is that any transactions that get removed as part of a rollback get immediately put back into the pool of pending transactions and can therefore get reapplied, provided they're still valid, even if you don't want them to. So let's suppose that Alice has actually spent some of the money, that some of the outputs, transaction outputs that she used for T1 differently in the new version of history that we transfer to as part of the rollback. So T1 isn't valid anymore, doesn't get applied. In this version of the world, well, Carol would never have seen T1 since T1 didn't get applied. Carol would never have chosen to pay Alice. But if T2 is still valid, and let's suppose it is, then T2 can still get reapplied. Now, this is terrible. What this means is Carol has just lost her money. Carol has paid Alice despite none of the preconditions that she was waiting for holding anymore. And this is like the archetypal thing we do not want. We don't want people to lose their money, either through bugs or through things that are these kind of complicated gotchas. We really would like people to not lose their money if they at least if they follow best practices. And this is just quite tricky to deal with because we have a situation here where Carol's beliefs about the state of the blockchain end up not matching what actually happens. And I've given you an example that has actual humans involved because to show this is something that can even affect humans who understand the system and know what's going on. And in this case, maybe they can resolve it. Carol can phone up Alice and say, "That was weird. Can you just send the money back and let's pretend that didn't happen?" Or you need to make a different transaction to pay Bob. But if you've got a computer programs are only as smart as you make it. So if you didn't account for this case, you're going to have a bad time. And so we would like to guide people towards doing this writing their applications in such a way that they're at least somewhat resistant to this kind of problem. And the general approach we're going to take is to follow an observation which is here pithily summarized by Runar, which is that constraints liberate, liberties constrain. And what that means is that the more you constrain some component of your system, so the less you allow it to do, the easier it is to work with, the more assumptions you can make, the easier it is to write tools that interact with it nicely, the easier it is to do things for it automatically because you know it can only be doing X, Y, and Z. And on the flip side, the more things it's allowed to do, the harder it is to reason about it or provide general purpose infrastructure. So what we're going to try and do is inject a little bit of discipline into how we write applications. So the first step is we're going to say, okay, we're no longer going to just assume that an application is just any program. Instead, we're going to insist that it be a deterministic, pure, replayable, sandboxed state machine. Now, that was a lot of adjectives, but what that really means is predictable and deterministic. So this means that we can just look at your application and we can say, if it sees the same input multiple times, it will produce the same output. And this gives us a nice kind of external view of the application state. We can say, well, if we crash and we lose everything, we can just feed it the same inputs, and that will put it back in the same state. Or if we need to synchronize them, we just synchronize all the inputs. Because it's sandbox, we know that we'll get the same result both times. It can't be like going off to Wikipedia to query the modification time of the Napoleon Bonaparte article or something. And so this is actually very nice. And those of you who are familiar with technologies du jour may recognize some similarities between this and the idea of event sourcing for programs. And that's no coincidence. It's a very similar lens on a similar problem. But this will make our lives quite a bit easier. It also means that we can start to move away from a world where users are responsible for doing all the interfacing to all of those different pieces of the world, to one where we can actually manage a lot of that for them, and we can run applications in some kind of harness that actually manages the interaction with the blockchain or with logging or so on for them. And generally, we move away from a world where it's all do it yourself, sink or swim. If you have to implement all these things, if you get them wrong, you lose your money, to one where there's more of a framework, and we can maybe make a few more promises about how if you follow the framework and you do what you're supposed to do, then things shouldn't go wrong, at least not in these ways. So what does this actually look like? We have our application, another gray box, except now it lives inside a sandbox, which prevents it from doing whatever it wants. And that lives inside the harness, which we call the Plutus application backend. Obviously, application's still got to talk to all the same things as before. It needs to talk to the wallet backend so it can actually spend the user's money. It needs to talk to actual nodes so we can actually submit some transactions. But now this is mediated by the application backend. So that does the actual talking over the node protocols or whatever, and the application has a simplified interface to that. Similarly, the application needs to talk to its clients, so the web app, some CLI, maybe some generic GUI inside a wallet front end like Daedalus, who knows? But again, we can forward that through the application backend in a nice, transparent way where we still see everything that happens and can do all the replaying stuff we care about. And then, pleasingly, a lot of the stuff like the logging and the monitoring or the management can then be done in a fairly generic way. At least we can log all the events that happen. We can monitor the amount of money that things are spending and so on, because we see everything that happens and how it happens. Another thing that's quite nice about this is that because the application doesn't interact directly with any of these components, we can just replace them with simplified mock versions of those that are run inside some kind of test driver, which is nice for a couple of reasons. One is that it means you don't have to run a full Cardano node to test your application, which is good. And two, because often you don't really want to run precisely the production version of these things, because you'd like to be able to control them in ways that you can't control the real node. You might want to say, please, can you just forget half of the transactions that I submit, because I'm trying to test the case where I have a bad network connection and I lose a lot of my transactions, and I want to make sure my application does the right thing. And if you've got a version that's designed for testing, then you can actually say things like that, which is quite pleasant. Okay, so this is given us a bit of a picture of what an application looks like. It's a slightly more restricted model, but one that gives us a bit of extra power because of that. But we haven't really talked very much about what the application does. The example I showed you was very dumb, all it did was just submit transactions that send money from one person to another person. You could do this on Bitcoin, you could do this on Byron era Cardano. You don't need any fancy features for that. So what actually are we looking for in our ledger? I think the answer to that is that usually what people are looking for is the ability to take some part of the logic of their application, put it onto the chain so that we can take advantage of the consensus properties of the chain, so that we've got some computation that executes in a trustless / trusted by all the parties way, so that everyone can assume that it's operating correctly. And if you put just enough logic in there, then that lets you do some things you couldn't do before. And we make a few changes to Cardano's ledger in order to support some of these techniques. And there's 3 that I want to draw attention to that we'll go through in turn. The first one is that we extend the basic Cardano ledger model, which is a UTXO model, to what we creatively call the extended UTXO model. The second one is that we go from a world in which we can only talk about ADA to one where we actually have native support for a wide variety of different assets which can be user issued, which actually opens up a lot of interesting use cases. And then finally, we enhance the scripting capabilities of the ledger. So actually, Shelley has basic multi-sig scripts, which I think is not that well known. So a lot of the basic functionality is there already, but we have a much more advanced scripting language for the features that we need. So let's go through those in turn. First of all, the extended UTXO model. So in the beginning, there was Bitcoin. And Bitcoin used the UTXO model to represent its ledger. And UTXO stands for unspent transaction output. And the reason for this is that the fundamental concept of the ledger is that transactions have outputs with money in them. So here we have a transaction, a gray box, it has an output, and that output has some stuff in it. And that stuff is just and that just hangs around in the ledger until somebody spends it. So if you want to get money, you've got to consume an output that's lying around, and then you in turn produce more outputs that move them forward. And so this is a slightly funny way of thinking about it in some ways, since you have these outputs are kind of real receptacles of the real receptacles of value, but it has a number of advantages, and this is the same basic model that Cardano follows. And of course, you don't want people to just be able to spend any output, right? Then there would be money, but it wouldn't be anybody's money. And so the simplest thing you can do is you can start locking outputs. And the simplest way of locking things is to use public key cryptography. So you attach some kind of key to the output that says this is the key this is the public key of the person who owns this. And then in order to spend that, you have to actually sign your transaction with the private key. And then we can say, yes, this transaction could only have been created by someone who controlled the key. Therefore, they have the right to spend the money. And this is often generalized a bit to a model that includes scripts, some more powerful programming language. And so instead of just having a public key, we actually have a program, which we call the validator. And instead of just having a signature, we have some kind of input, which we call the redeemer. And the validator is given the redeemer as an argument, and it says yes or no. And that's how you decide whether you're allowed to spend the output. And this is actually how Bitcoin works in practice. Bitcoin has a script language, and even simple public key locked outputs are implemented with scripts. The script just says, is this a valid signature for the corresponding public key? But it is nonetheless a script. They're all implemented that way. We extend that even further. So we add 2 more things. The first thing we do is we add a bit of data to the output. We call this a datum. Datum is the singular of data, which nobody ever uses, but mostly it's a word that sounds like data, but isn't data, because data is extremely overused for just about everything. So this is a jargon term for the bit of data that goes on an output. And this is quite handy because it's a nice way to attach extra information to outputs without modifying the validator, because the validator typically determines the address of the output. So ideally, you don't want to mess with that. This is very useful for carrying state, for example. The other thing is that the validator gets to see this vaguely named context. And this is the context in which validation is occurring. And so what this usually is the entire transaction that's being validated. So what this means in practice is that the validator can see the entire content of that transaction, which means it can see how you're going to spend the money. So if you just give someone a redeemer that's the signature, you say, well, here's the signature, check the signature is fine. You have no idea, and then you can do whatever you want with the money in the rest of the transaction. The validator can't tell. But we actually let the validator look at that, so it can see the other inputs, it can see the outputs, and in particular, this lets you do interesting things like assert that there is an output locked by the very same validator, which has some of the money in it or something. And this lets you create chains of transactions with the same validator, which is key for doing more advanced patterns like state machines. And this is not a super new idea. The similar idea with things like Bitcoin covenants, but the particular way that we do it is slightly unusual and very powerful because you can see absolutely everything. Okay, so there are two key takeaways from this. The first one is that outputs carry some additional data, and the second one is that the validators are able to inspect the context of the validation. Okay, so let's talk about multi-asset support. So to start with, most distributed ledgers begin off tracking one thing, and that is money, some kind of money. In Cardano, it's ADA, Bitcoin is Bitcoin, the usual. But what they often realize after a while is it'd be quite nice to be able to track other kinds of things. You've got this big system for tracking stuff, where it goes, who owns it, but the only stuff you can talk about is money, and actually you'd like to talk about other things. Hats, swords, shares, I don't know, all kinds of things. And these are often called tokens or different assets or something similar like that. And we are adding something very similar to Cardano. So, let's go back to our transaction and its output. Here's a transaction with an output, and that output contains 5. 5 what? ADA. That's the only thing there is. There is no other kind of thing, so it's just a number. So the kind of value that our ledger deals with is just numbers, meaning ADA. So it's just a quantity of ADA, but that's implicit. Okay, so we've realized that we'd like to track other kinds of things. So we think, okay, let's add like a tag of some kind that tells us what kind of thing it is, what the unit is. So we'll say we have 2 hats, not just 2, and then we could have 2 ADA also. And that way we'll be able to keep them apart, and we'll say, well, hats and ADA are not fungible with each other. They're separate things. And this is good. So we can say, well, okay, maybe we'll call this like the asset. And so we have for some number of assets, and for each asset we have the quantity of it. But once you start thinking about this for a bit, you realize that often you have a bunch of assets that kind of go together. Typically, they're controlled in the same way. They have the same owner, this similar policy for managing them. I'm saying vague things here because I'm going to make them precise later. But for example, suppose you run a game, maybe your Fortnite, and you're issuing tokens that reflect items in the game. So you have hats, you have swords, and the rare sword Excalibur, of which there is only one. It's very valuable. And you may want to group all these together under some kind of policy domain. In this case, my game, and keep all of those separate from any other ones. So same as before, but I'm going to call this top level thing a policy for now. I'll explain why in a moment. And this policy, it's actually the part of the clever bit of the way this works is the policy is not just some arbitrary string. It's actually a hash, and it's the hash of a script that is in fact the policy. So that's the clever bit about how the system works is that the linkage between a representation of some actual tokens belonging to some policy domain and the policy is baked into the representation of it. So we don't need to do any separate registration step to set up that association, and this actually makes it possible for us to do this in a very lightweight fashion. Before I talk a bit more about the policy, I just wanted to point out that I'd kind of said this implicitly. We do want to mix these things in a single output. You don't want to have your output be only ADA or only Fortnite tokens, you would like to be able to mix them together freely. So actually, the real value type is, a bundle of these things. So once we've kind of, having gone through all that, what we eventually end up is, we say, it's like a map from policy hashes to asset types to quantities, which feels like a lot of stuff, but I hope I've given you an idea for why it is actually useful to have all that structure. Okay, so let's talk about the policy. And the policy is intimately related to how you actually get these things in the first place, because there are no hat tokens on Cardano today. These things are going to have to come from somewhere. Where do they come from? Well, you have to mint them. The way you mint tokens is using this forge field on transactions. So inside the forge field, you can just put some value. It can be positive or negative, in fact. And negative, if it's negative, then that corresponds to actually destroying or burning tokens. When you forge some tokens, then that's just added to the balance of the transaction. So if you created some, you can then spend them in an output. If you destroyed some, then you have to provide them in an input. Otherwise, the transaction won't balance. But surely there's some control in this, right? Like, we're not just saying anybody can do this at any time. And the control is that you also have to provide in this forge scripts field a script S whose hash is the policy. And that script will be run, and it'll be given its context will be the transaction that you're doing, and so it can check whether you're allowed to do it. So a very simple example might just, again, rely on public keys, and it might say, well, if it's signed by this particular key, then they can do whatever they want. They can create or destroy tokens as they like. And this would be good enough for, say, the Fortnite tokens, because ultimately they control the game itself, and this is supposed to be a representation of the game. So they have ultimate control over the truth of the matter. So giving them total control over the tokens doesn't expose you to any more trust issues. So, but you could also do much more complicated things if you want, if you're doing some kind of fancy algorithmic stablecoin or something. And there's a little extra complication because actually the forge scripts get a redeemer and a context as well, but fundamentally the picture is how I've shown it to you. So the key takeaways from this are that A, we get this nice support for native token bundles, and B, that we have this really lightweight and straightforward forging process. So you don't have to do a kind of global registry of a new currency or anything. You can just forge it immediately, and this actually lets you do a lot of interesting things, which I'm not going to go into too much in this presentation, but you can read about more elsewhere. Finally, more powerful scripting. So our scripting language is called Plutus Core. Plutus Core is a small functional programming language. It's System F Omega with recursive types for those of you who like that kind of thing. And it's basically our on-chain assembly language. So that means that we're not expecting anybody to actually write this. That would be awful. It's a compilation target. So you're going to write some other language and compile it into Plutus Core before putting it onto the blockchain. And crucially, it's not very novel, by which I mean this is all programming language theory from 40 years ago. And we regard that as a virtue because it means that hopefully we're not reinventing the wheel and we won't make lots of stupid mistakes, and also we can piggyback off everybody else's work thinking about these kinds of language. And it's the resulting thing is boiled down very small. The evaluator fits on a napkin, as you can see there. So that's kind of all there is to say about that, but it works reasonably well in that respect. That's kind of all there is to say about that. So we now know what an application is. We know what it means for it to interact with Cardano and how we're going to enable it to do interesting things with Cardano. We also want people to write these things. They have to actually produce applications somehow. And ultimately, this is not going to be very surprising. We are providing an application platform. We're going to give you libraries and SDKs for writing applications. And to begin with, the support is basically all going to be in Haskell. So it's going to be a Haskell SDK. Maybe one day there will be SDKs in other languages, but I'm not making any promises right now. And this provides quite a lot of useful functionality. So one of the big things is that you've got to actually produce these Plutus Core scripts somehow. And we have some quite cool compiler technology that actually lets you compile Haskell itself into Plutus Core. I put a little exclamation mark there because that's actually quite difficult. So quite pleased that that works. It actually works very well. Indeed, because of that, and because of the fact that the rest of the application is in Haskell, you can just write all this together. You can write it in the same file. You can even share types and functions between the on and the off-chain code, which is actually very nice. And then obviously we also provide libraries for actually writing an application that follows the framework and can speak the protocols correctly and so on. So that's all as you'd expect. The other development tool that we provide is the Plutus Playground, which some of you might have seen in previous presentations. And this is basically a kind of an online development environment, not as fully fledged as you'd have if you download and use the libraries locally, of course, but great for getting started. And it has some nice things like you can create your test cases graphically and by dragging things around and then run them and visualize the output a bit, which hopefully, the local stuff will also get the fancy UI up to par. But it's a nice additional tool. And the final thing we need to talk about is the users of these things. And users have a lot of needs. So you've got to, if you want your application to be used by other people, you've got to actually get the damn thing onto their computers. You've got to distribute it somehow. You've got to update it when you push out new updates. They've got to be able to manage it. They've got to be able to, control how much money it's using, and they've got to audit what it's doing so they can trust it. There's got to be UI for it, probably graphical UIs, maybe CLI interfaces for your power users. They just need a lot of stuff. And this is all really work in progress at the moment. So hopefully there'll be more to report in the future, but at the moment, well, we don't really have enough users to say, but I hope that this will develop a lot as time goes on. And that's really the picture. So I can now show you this somewhat ferocious architecture diagram, which more or less covers basically the things that we've discussed today, and a couple of links for further reading. So there's the Plutus Platform technical report that also covers fairly similar ground, and also one of Manuel's talks from Lambda Jam last year, which is still valid and pretty good. And with that, I'm going to hand you over to Jan, who's going to do a bit of a demo.
Thank you, Michael. I'm Jan Müller, and I'm going to show you the demo now of the application platform. Okay, this is the Plutus application platform. It's running on my local machine here, and it's connected to an emulated node that's also running on my machine. And that node is validating the Goguen transaction that we have, and it's just adding new blocks to the blockchain while it's running. And when you open the application platform, you get the list of the contracts that you've installed. On this instance here, I've installed two contracts. One's called Atomic Swap and one is called Currency. We will get to the Atomic Swap one in a second. For now, I'm going to use the Currency contract to create my own tokens on this local blockchain. So I'll click Activate, and Activate starts a new instance of the contract. Once you've installed the contract, you can have any number of instances of it running. And I'm going to give it a name for the new currency, my token, and an amount. And when a contract instance is running, it can query the user for input at any time. Very similar to how it was handled in the playground where we had endpoints. You get a simple UI that's generated for the data types that the contract expects. And in this case, there's a contract that's asking for a token name and the amount, which is going to be 1,000 units. So I'm going to click Submit. And this will trigger a number of transactions sent to the blockchain and validated. And that's going to take a few seconds. And while that's happening, I'm going to start a second instance of the application platform. And then later on, I want to trade these tokens that I just created. with this other instance. So 8085. This is another process that's running the application platform. It's not connected to the first application platform in any way, except that they're both talking to the same node, so they get a view of the same blockchain. And in this instance, I've only got one contract installed. But now let's look at the blockchain tab. Here we can see the transactions that are currently in the chain. And because this is a small emulated chain, there's not much happening on it. We only have 2 transactions so far. The first one, we click it, it shows up the details. The first one is the initial transaction that generates all the ADA that we have in our testnet. And you can see the outputs of these transactions on the right-hand side here. The green boxes are public key addresses. And this transaction here pays 10,000 Lovelace to each of these 10 public key addresses. And these are the addresses of the agents that we emulate here in this testnet. So we've got 10 addresses, each with 10,000 ADA. And we've got a second transaction that was that's part of the creating the currency process that's currently going on in the other application platforms. So we can already see it on the chain here. But this one does not create the currency yet. There will be another transaction that does that. This one is doing some groundwork for it. So we can see that it has 2 outputs, and in particular, it produces a script output, the orange box here on the right, which locks just one Lovelace blocked by the script address. Now, if we go back here and refresh, we should be able to see, yes. So we're looking at the same blockchain, and we can see that the third transaction has been added. And this is the transaction that actually creates the tokens. And its inputs are here on the left-hand side. That's the orange box, the script output that was produced earlier. It's spent by this new transaction, and on the output side, we see it pays some value to this public key address, and the value that it pays is 1 Lovelace and also 1,000 units of my token. So this is where we've created the currency. And the hash here at the top, this is the policy of this asset, of this that regulates when new tokens of this currency can be forged. And we can also see that there's a blue box here below the transaction body that details the values that were forged by this transaction. So we can see again, this is the script address, the script hash, and it created 1,000 units of my token. And the fact that the script input here was spent is quite important, because the hash, this input here is included in the policy hash of the token. So if anybody else wanted to create more of my token, they would have to spend the same output again, this output here. But they can't, because the output can only be spent once, and therefore we have a guarantee that there will only ever be 1,000 units of my token. So the total supply of this currency is very limited. There are only 1,000 units. We can, of course, write more complicated monetary policies in Plutus, but this simple one just says forge 1,000 units exactly once. Nobody else can do it again. And after that, there will be 1,000 units of this. And if you go down in this view, we will see the balances in the blockchain. And we have the 10 public key addresses of the agents that we have and the script address. There are currently there's 0 value locked at the script address, but there are 1,000 units of my token locked at this public key address. And that's the address of the agent that ran the create currency contract. So now let's trade this currency. I want to give some of these tokens that I just created to the other agent here, to this process that's running in this tab. And to do that, I want to use a contract. And I want to do the contract because I want to be sure that the money is actually exchanged. I don't want to send it first and then have to wait for that person to make another transaction. I want them to be paid at the same time. I want both amounts to be paid at the same time. And that is what the atomic swap contract is for. So I activated that. And we will have to do this on both sides. So first, let's put in the Lovelace amount, 100 Lovelace. The currency symbol, which I just copied, this is the hash. The token name is my token. And let's say 100 tokens of that. And party 1 is wallet 1, party 2 is wallet 2. And we have a deadline of, let's say, 2000. And we click submit. While that's loading, we have to do the same on this side here. So 100 Lovelace, this currency, my token, 100 units, 1, wallet 2, and deadline 2000. And let's click submit. Okay. And while this is happening, I'm going to explain the atomic swap contract a little more. I'm going to explain what it does. We can already see that there's a new transaction. So previously we had 3 transactions, and now this is the 4th one, and that's part of the atomic swap. And the 4th transaction here, we can see that it pays 100 units of my token to a script address, the yellow box here, 773. And this is the script address of the swap contract. And the second party, so the one whose tab we're currently looking at, is going to create another transaction that also pays some money to this script address, to the same address, 773, but it will pay 100 Lovelace. So that when the second transaction is in, we will have 100 Lovelace and 100 my tokens at the address. And then to spend them, we're going to have a third transaction, which you might be able to see now. Click refresh. Okay, so let's start with this one. This is the one that pays 100 Lovelace to the script address 773. And at this point in time, slot 481, if we look at the balances, we can see that the script here is locking 100 Lovelace and 100 of my tokens. So these are currently at the script address in 2 different outputs from 2 different transactions. And they are spent by that transaction. So we can see the last transaction here. It takes the 2 script outputs. They both have the same address, but different amounts, and pays them to the public keys that were specified. And the validator script of this output, it makes sure that the inputs here can only be spent if these exact outputs are in the transaction. So if 100 my tokens go to this public key address, the first one, and 100 Lovelace go to this public key address, the second one. And that's how the contract enforces that the swap actually takes place, that the trade takes place as was agreed. And we can do this without relying on a third party or an exchange or anything like that, just using the on-chain contract and the multi-asset ledger that facilitates this. And just a final look at the balance sheet here, we can see that this public key address, third one from the top, has 10,100 Lovelace. So it has 100 more than it had at the beginning. And it has 900 my tokens left. And then the first address here, 03D, has only 9,900 Lovelace, but it received the 100 my tokens. So we use the contract to make sure that everybody played by the rules of this payment. And if one of the parties hadn't made their payment, then the other party would have been able to claim a refund from the contract without even involving the other party. So we didn't have to trust anybody, just use the contract to do the on-chain exchange. And that concludes the demo of the application platform. Thank you. Okay, thank you all for watching. We're looking forward to your questions.